Okay, so one of the things you have to be able to do in this unit is interpret a climate graph. Okay, on your unit exam, I will ask that by saying, here's a climate graph. What biome does it go with? Okay, so a biome is an ecological region on Earth. You actually learned those like back in junior high, maybe like grade 7 or something like that. Okay, but don't worry, I'm going to go over them again. Okay, that's going to be Monday's lesson. Okay, so I'm going to go over biomes on Monday, and then you're just going to have to be able to go, okay, so this climate graph says that the climate here is like this, and that means it would fit best with this biome. So if I had a climate graph, but there was like almost no precipitation, and the temperature was like 30 degrees all year long, okay, you would say this is probably an equatorial desert. Okay, because the climate graph indicates there's no change in temperature, or basically no seasons, and almost no rainfall. Okay, that fits with a desert biome because they are typically, or an equatorial desert biome because they are typically hot and dry with no distinct seasons. Okay, conversely, if I had, something like this one where I had a temperature line that is bell curved, okay, which means that part of the year it's cold and part of the year it's warm, okay, this is not something that's near the equator, okay, because that means there's different seasons. So this would be further from the equator, right? And it doesn't ever get very warm, okay? It's like, 18 degrees in the warmest month, okay, on average. Okay? Doesn't mean it's 18 degrees every day on average, okay? And in the coldest months, it's down into the negatives. Okay, so this is definitely, mid-latitude to maybe even further than that. Okay, and if I'm looking at the rainfall, which are the bars, okay, I'm seeing that there's significant precipitation. Right? In the driest month, they get 100 millimeters of rain. Okay, like we get 100 and some millimeters of rain in our wettest month here. Right? So this is considerably wetter than Calgary. Okay? But I would say that probably similar in latitude to Calgary, okay, given the temperature, but much wetter. So I would say that this would probably go with, probably like a deciduous forest biome. Okay, so that might be more like the Maritimes or something like that, okay, or a mixed forest biome or something like that. Okay, everyone kind of follow me there? That's what you would be expected to do. You've got to look at the graph and tell me what it says. Okay, that was me saying, well, this has seasons, so it's probably far from the equator. Okay, it doesn't get really warm. It doesn't get super cold. Okay, and there's fairly steady, significant rainfall. That says, okay, I'm going to get 3 marks out of 5 because I correctly interpreted the climate graph. Okay, and then you tell me it goes with this biome because there would be your other 2 marks. Okay, so it would be a 5-mark question. Does that make sense what you'd be expected to do? Okay, so is interpreting a climate graph like a super difficult thing? Okay, so we're going to go over that today. And then tomorrow, we're going to finish up the latent heat stuff that we started on Monday. Friday, we're going to do our unit exam review. I know that seems weird because I haven't taught the biome lesson, but I can't teach the bio lesson in 60 minutes. Okay, so we're going to do the unit exam review Friday. Monday, I'm going to teach you biomes, which is just memorization. Okay, and it'll seem familiar because you've taken it before. And that lesson will be me starting at 8:37 and talking really, really fast until 9:58. Okay, because it takes me a whole 85-minute period to teach that lesson if I talk real fast. Okay, and then Tuesday will be your unit exam. Okay, Wednesday we'll go over the Unit 4 exam, and we'll start reviewing for your final. And then Thursday will be another final exam review day, because I was mistaken on Monday. You do have school on next Thursday. Okay, so you do have. I saw that grade 10 exam and I got confused. So you do have school next Thursday, okay, and we are going to do final exam review on that Thursday. Okay, I'll tell you more about how that's going to look next week. Okay. Questions on the plan for the remainder of the semester? Because it's coming to an end fast, and we're cruising right along. Okay, so what I want to do with these climate graphs is see if we can pick out which ones might go together. Okay, or which places which climatogram should go in, let's say, a group together, because this is kind of what you would have done in your climate graph activity. Okay? All of these climate graphs are from Canadian cities. Okay? But I've scribbled out the names. Okay? So if I'm just looking at them, okay, like let's say I'm looking at the first two here, are they fairly similar? Like just at first glance, they have a very similar shape, right? Upon closer inspection, if I look at the actual numbers, okay, so in this first one here, if I'm looking at the temperature line, okay, in January it's about -6 degrees. Okay, and on this one, in January, it's about -4 degrees. Okay, February gets a little bit colder. February gets a little bit colder on the other one. Okay, and they generally trend upwards into July, flatten out for August at around the same temperature, just a little more than 15 degrees, and then they plummet down, okay, for the fall and winter. So yeah, their temperature line is pretty similar. Okay, and their rainfall pattern is also pretty similar. So on the right-hand side, I can see the precipitation in millimeters. Okay, these numbers are all very, very similar. Okay, so would it be logical to assume that these two cities are probably affected by the same factors that affect climate? Okay, so that's how that activity was supposed to go. It was supposed to be about, okay, find ones that are the same and then determine what factors affect the climate for those cities the most. All right, so those two definitely go together. All right, if we're looking at some of these other ones, this one's a little bit colder, and maybe just a little bit drier, but it's still pretty close to those two. Okay, so should those three probably go in a group together? Okay, so for the reveal here. That's Halifax, St. John's, Newfoundland, Charlottetown, PEI. Yeah, those should definitely go in a group together. They're all pretty close to each other. Okay, and they're all on the east coast where they would be affected by the North Atlantic current. They're all about the same latitude, same distance from the equator. They're all coastal cities, so they have the same altitude. Okay, they'd have the same kind of prevailing wind patterns. None of them are near mountain barriers, okay, or anything like that. So they would all have the same factors affecting their climate. Everyone okay with that idea? Now, what about that one? I mean, obviously the format of the graph is different, okay? But the shape of the graph is also a bit different. Okay? This one here, the coldest temperature is above freezing. Okay? And the rainfall, even though its shape is the same, is considerably higher. Okay? Instead of the wettest month being 160, now it's like 375. Okay? So this place is a lot warmer and wetter than the other three cities that we've looked at. So it definitely wouldn't go in a group with them. Okay? Given the data on that graph, where do you suppose that graph comes from? I would say certainly west coast of Canada for sure. Okay, it could be Vancouver, maybe Victoria, okay, something like that. They would have very similar climates because they rarely get below freezing and are considerably wetter, okay, than here. I don't know if Vancouver would necessarily be that wet, but let's see. Not Vancouver, but west coast. Okay, Prince Rupert is actually one of the wettest places in North America. Okay, it gets tons and tons of rain off the Pacific. Okay, so looking at this one here, this one's got significant winter, drops below zero. Okay, rainfall is pretty steady on this one. Okay, the other ones all kind of change throughout the year, but this one's pretty steady. Okay, it goes, the driest month is about like 50 millimeters, the wettest month's about 85. Okay, that's happening in the summertime. It certainly wouldn't fit with the coastal cities. Okay, Okay, it looks different than those. The temperature line's similar, but the rainfall pattern is wrong. Okay, so it definitely wouldn't go with the coastal cities, and I don't think it would fit in a group with Prince Rupert either. It's not nearly wet enough for that one. Okay, so don't know if that one goes together. Would this one and this one go together? Definitely not. Okay, they're significantly different as well. Okay, this one, look how cold it gets. Okay, like in January it goes down to, you know, between -15 and -20, but in the summertime it's way up by 20. Okay? And the rainfall follows the temperature. The wettest month in that place is probably June. Yeah, it is, and significantly June. Right? What does that sound like? Here. Yeah, that sounds like here to me. Or certainly a prairie city, okay, to be certain. It's a prairie city, okay? It's not Calgary, but it's a prairie city. If you actually look at Calgary's June rainfall is a spike. Like it is significantly higher than all the other months. Okay. And that one was Ontario. Okay. Most of your central Canadian cities would have climate graphs that look like that because they're temperate deciduous forest. And in order to have that, you have to have pretty steady rainfall throughout the year, and obviously milder winters than we have on the prairies. Okay, that one looks like Winnipeg's, agreed? Okay, pretty similar, probably has the same factors affecting climate. Okay, it's pretty dry, it's drier than Winnipeg actually. Okay, so that's for Regina, but they would definitely go together, still affected by the same things. Mountain barriers would be creating a rain shadow, which is why they're significantly drier. Okay, they're not near an ocean that can regulate their temperature, so they get significant swings in temperature between summer and winter. All right, well, those two definitely don't go together. Okay, in fact, the rainfall pattern is a mirror image of that. Okay, and if we look at the temperature, it doesn't drop below freezing. Okay, so Margot, would this one be more like what you thought before?
Yeah.
Yeah. Okay, it's quite a bit drier than Prince Rupert, right? Prince Rupert had really high rainfall, like 300 and some millimeters. Okay, this one is much more reasonable. Still too wet to be a prairie city. Okay, but more rainfall with dry summers. That's the opposite of us. Okay, in Calgary and on the prairies, we have wetter summers. Okay, here they have drier summers. Right, and the reason for that is they get rain in the winter when we're getting snow. Right, and just so you know, 10 centimeters of snow is the rainfall equivalent of 1 centimeter of rain. Okay. So even though we always think, oh, we get so much snow, it's so wet in the wintertime, it's really not. Okay? When we get 20 centimeters of snow, that's how much rain we would get in an hour in a thunderstorm. Okay? Like it's just not a lot of moisture. It piles up because it's all light and airy, but it doesn't represent a lot of water. Okay? So that'd be Victoria. Okay? Those two go together? Definitely. Okay, this one's a bit different. Right? It definitely gets pretty cold. Right? So it's either far from an ocean or it's really far from the equator. And the rainfall pattern goes up in the summer and fall, oddly. Okay? And then in the other months it's pretty steady, but there's not a lot of it. Okay? Even though the bars look really tall, the scale can be misleading, and that's something you need to watch for on a climate graph. Okay? I can make a desert look like a tropical rainforest by making a stupid scale. Okay? Like this scale only goes to 40, this scale goes to 180. It makes this one look as wet as that one, but they're not. Okay? So always make sure you look at the numbers. Okay? Otherwise it can be pretty misleading. So this place is pretty dry and pretty cold. 40 millimeters of rain is that much. Okay? That's the wettest month in that place, so it's pretty dry and pretty cold. That fits. Okay. Everyone all right with that? Following how this would go for you? Okay. So the big thing on the test is be able to do what I've done on every single one of these. Describe the climate. Okay. There's a big bell curve, so it's far from the equator. Winters are cold or not. Okay. In this case, the winters are not cold. There's a winter, but it's not cold. Okay. And the rainfall is distributed so that summers are dry and winters are wet. Okay. And obviously there'd be no snowfall in this particular place. Okay. All of the precipitation would fall as rain. That's you telling me I can interpret the climatic. Okay. Okay. Does that one look similar to the one we just did? Yeah, I would say so. And it's super cold. Okay? The coldest months are down in the negatives, way down in the negatives, and the warmest months are single digits. Okay? So this would be a very northerly biome, okay? A very northerly location. And again, the scale of the precipitation makes it look wetter than it really is. And the wettest month is 70 millimeters. Okay? I would say that the bulk of their precipitation falls as snow. Okay, which again, doesn't represent a lot of moisture. Okay, would seem to fit. All right, on this one, do these go together? No, I mean, they have kind of a similar shape, but the numbers are all wrong. Okay, this one here, okay, the precipitation's on the left for whatever reason, okay, but it's a little bit wetter, not a lot. It's a fairly dry place, but the temperature is considerably different. Okay, we're talking, cold winters, but not extreme cold winters, and reasonably mild summers. Okay, and June is a spike. Okay, that would fit with like Winnipeg and Regina and those cities. Agreed? What city is this? That's here. Okay, like I said, in Calgary, June is a spike. Okay, June is by far our wettest month, right? And so we get by far the most rainfall. That's when thunderstorm season starts. Okay, and that's why whenever we get flooding here, it happens in June. Okay, late June, early July. That's the high water season here, because runoff is happening, and we're getting the most rain. All right. So that one's got, well, it's about the same moisture level as Calgary, and the temperature line's a little bit colder than Calgary. Okay, drops down a little cooler in the winter, about the same in the summer. Okay, but its precipitation pattern is shifted just a little bit. Okay, it's less about June and more about July and August. But still close enough to be a prairie climate. Okay. Why does Edmonton end up so much colder than Calgary?
It's further north.
Part of it. And what else do they not get that we do? What? Oh, I thought you put your hand up. Yeah, they don't get Chinooks. What causes Chinooks? Mountain barriers. Is Edmonton close to the mountains? Not as close as Calgary. Okay, Regina doesn't get Chinooks. Winnipeg doesn't get Chinooks. That's a Calgary thing. Okay? It's a Calgary Lethbridge kind of thing. So that's why we would have a more mild winter here than they would in Edmonton. All right. So this one here, it's very cold. Okay. Gets just above 10 in the summer, but down minus 28 or so in the wintertime. And precipitation, it is pretty dry, right? The wettest month is about 65, 70 millimeters of rain. Most of them are considerably less than that. Okay, this would not be a prairie city, would you agree? Okay, would it fit with like maybe Whitehorse and Iqaluit and places like that? That's pretty northern Manitoba. Okay, sometimes you get climate graphs that look like this. I wouldn't put one like this on a test because it's hard to read. I just couldn't find any ones for these cities that looked like the other ones. Okay, so the middle purple line here is the average daily temperature. Okay, and so we're looking at, you know, in the summertime about 18 degrees, in the wintertime about minus 20. Okay, and rainfall does go up, okay, throughout the year, but it's never very high. Okay. So kind of a Great Lakes climate a little bit. Okay. So this is Thunder Bay. Do these two go together? Temperature-wise, they're pretty similar. Precipitation-wise, the one on the right's a bit wetter. Okay. There might be an argument if you were being really picky to have them in separate groups, but geographically speaking, they're pretty close. Okay. One would get more of an effect from the Great Lakes than the other. Okay, and then this one here, this one's shifted considerably towards the fall for precipitation, and it's quite a bit drier. Okay, and it's pretty cold, down into minus 30 here. Okay, so would that be more of an Arctic one? Okay, enough joke. About this one, we got pretty even precipitation, but it's not very high, and our temperature line says that it's not very warm in the summer, but also not terribly cold in the winter. Okay, so fairly northern part of Labrador. The ocean is what would be regulating the temperature there. That's why I wouldn't put it in the same group as like Nunavut and Whitehorse and places like that. Okay. All right, and last one. That place is really cold. Okay, like down minus 34, 35. Warmest months are like 4 degrees Celsius, and it's dry. Okay, we're talking about precipitation being less than 30 millimeters, okay, a month. That's the wettest month right there. Okay, also pretty dry, and I'd say the bulk of it would fall as snow. Okay, those are the kind of things you want to include when you're interpreting the climate graph on the exam. Okay, all right, making sense? Okay, so on Monday, we talked about specific heat capacity, and we did the E equals MC delta T problem solving. Okay, and then I introduced this, which is the heating curve of water. Okay, and I was talking about how for any material, there's going to be a heating curve. It's not going to look exactly the same, but they're all going to have some kind of heating curve. Okay, and they do that because for all materials, they exist in 3 states. Okay? At certain temperatures, they'll exist as solids, and at certain temperatures as liquids, and at certain temperatures as gases. Okay? Now, that's not true for all materials. There are some materials like carbon dioxide that sublimates directly from solid to gas. Okay, so if you've ever seen what happens with dry ice, right? It just goes straight from solid to gas. Okay? It skips the liquid phase entirely. Okay, this is the heating curve for water, which is of course the most important thing for us because it affects climate. It's part of those factors that are part of that, proximity to oceans, all of those kind of things. It's also part of latent heat as an energy transfer mechanism on a global scale. Okay, so what we want to do is look at how we can kind of determine how much energy would be possessed by a certain amount of water in a certain condition or state. Okay, so if I have a block of ice, so let's just say I've frozen a big block of ice, and it's 1,000 grams, so it's a kilogram of ice. Okay, that's 1 liter. Right? And I have it at minus 25 degrees. I put that block in a pan and turn on the stove. What's going to happen to the block? Before it melts, it has to do something. It's got to warm up. Right. Ice isn't going to melt until it gets to 0. And then the ice-water mixture is going to stay around 0 degrees until all the ice is gone. Okay? Because thermal potential energy and thermal kinetic energy cannot change at the same time. You can only change one at a time. So when you're adding thermal energy to something, you're either making it get hotter, changing its temperature, and thus its kinetic thermal energy, or you're changing its state, okay, which is how far apart the particles are, and that's the thermal potential energy. Okay? So in order to get ice to melt, I have to first increase its kinetic thermal energy so that it gets to its melting point. Okay? Now, in this part of the graph, as we said, the kinetic thermal energy and thus the temperature is changing. We have a formula that will calculate how much energy would be required for that to happen. That's the one we talked about on Monday, E equals mc delta T. That calculates the change in kinetic thermal energy. Okay? So in this case, I would have 1,000 grams of of ice that is being heated by how many degrees Celsius? If I start right here and I go to here, what's the change in temperature? 25 degrees. I go from minus 25 to 0. Right? So, would I be able to calculate the amount of energy knowing I have 1,000 grams, I know it's ice, and I know the temperature change is 25? Absolutely. Okay? A similar thing is happening in this part of the graph. Okay, so right here, I'm also increasing the kinetic thermal energy, but now I have liquid water. Okay, and so as I add that thermal energy, the temperature would change, and again, I would use E equals mc delta T to calculate how much energy would be required to heat 1,000 grams of water from 0 to 100 degrees Celsius. Okay? The other place on this graph, okay, where this is happening is up here. Okay? At that point, I have steam. I no longer have liquid water, I have steam. But if I add thermal energy to the steam, it's also going to change temperature. Okay? And so I would again be able to use this formula. There are 2 points in this heating curve where the temperature doesn't change, but I continue to add energy. Okay? Those are the places where water changes state. So it's melting point and it's boiling point. Okay? Now, here at the lower end, okay, is where the ice melts into liquid water. I can't use this formula to calculate how much energy is required for that step. Because first off, it's changing from ice to water, and they have different heat capacities. And secondly, what's the temperature change there? What's the temperature the whole time that ice is melting?
0.
0. So what's my change in temperature?
0.
0. Well, that's going to tell me I didn't have to add any energy. That's not true. The graph clearly shows heat added. I put energy in. Okay? So that's not going to work. I need a different formula to calculate how much potential thermal energy has been added. Okay? That formula for this part is E equals m times LF. Okay? M is again the mass, so it'll still be 1,000 grams. LF is the latent heat of fusion. It's the amount of energy per gram that is required to melt ice. Okay? That number is 333 joules per gram. Okay? And on Monday I was telling you, if you've ever made a snowball with your bare hands, you know that that requires a lot of energy because your hands get very cold. Okay? They get very cold because for every gram of snow that melts while you're making that snowball, your hands donate 333 joules of thermal energy to the snow. Okay? Does that make sense to everybody? Okay? So that's why your hands get so cold. All right? So if I wanted to calculate how much energy was required there, I'd just take the mass and multiply it by this number. This is a pretty easy calculation. Okay? A similar thing is true here. Now this is the biggest part of the graph in terms of energy. Okay? It's where the most energy is put in. More almost than all the other sections combined. Okay? That's converting liquid water into water vapor. Okay? That's going to require this formula. E equals mLV. LV stands for the latent heat of vaporization. Okay? That number is 2,260 joules per gram. And it takes a huge amount of energy to evaporate water. Okay? So this is why when moisture comes to us from other places as water vapor and then condenses, why that's such a huge energy transfer mechanism. Every gram of water in a cloud carries with it that much energy in terms of latent heat. Okay? When it condenses back into liquid water, that much energy is released as sensible heat. Okay? That will bring up the temperature of the area where it condenses. That's how it's bringing energy from the equator to more northerly areas. So if the water evaporates from the ocean near the equator and then moves north, it's bringing tons and tons of energy with it. Okay? Not as sensible heat, not as heat you would feel, until it gets here and then condenses. Okay, everyone all right with that idea? That's why we said before, latent heat is such a huge energy transfer mechanism. All right, so I also said to you on Monday that you've probably heard you get burned worse by steam than you do by water, even if they're the same temperature. Okay, well, that's because every gram of steam has this much more energy than its liquid water counterpart. Okay? Is that a lot? Definitely. Okay, it's a ton of energy. Okay, and that's why, like, I think I also used the example if you were at Stampede, right? And it's like super hot, and they have those misting stations that you can walk through. Okay, the mist lands on you, and then immediately it starts to evaporate. Okay, where does it get the energy to evaporate from? From your body. Okay, so for every gram of water that evaporates off your body, you shed 2,260 joules of energy. Okay, that's a very effective way to cool you off. Okay, okay, that's why sweat works. Okay? It's why we say in Canada so often, in the wintertime, dress in layers. The worst thing you can do is sweat when it's cold. Okay? If you get your layers wet with sweat, as soon as you stop working hard, that sweat's going to start to evaporate, and it's going to take energy from your body to do it, and you're going to get hypothermia really quickly. Okay? So if you're outside, you're shoveling a bunch of snow or whatever, okay, take off some of those layers. Okay? That way, if you get one layer really sweaty, you can just take it off and put on a dry layer instead. Okay? Or you just took off enough layers that you didn't get really sweaty, okay? And that's smarter than just wearing a parka, okay, and getting all wet. Because once you're not working hard, you're going to get cold really fast. Okay? All of these things are governed by these kind of simple physical laws. All right? Making sense? Okay. So if I put ice cubes in a drink, that keeps it cold. Yes? Keeps it around freezing. Where does the energy go? Energy is coming in from the surroundings, but the drink stays cold because the energy is going into what? It's going into the ice. The ice is absorbing it. Okay? The ice is changing state, but not changing temperature. Okay? So it keeps your drink cold. Same as a cooler. Right? You wouldn't fill a cooler with cold water. You'd fill a cooler with ice. Okay? Why? Well, because the ice starts down here. The water, even if it's like at 1 degree Celsius, starts here. Ice can absorb this much more energy than liquid water. Okay? So it makes more sense to fill it with ice. Plus, you don't want to throw all your, bread and stuff in water. Get all soggy. Okay? So it makes more sense to use ice. It absorbs more energy. Okay? Everybody all right with that? Okay. So, the latent heat of fusion for water is 333 joules per gram. You do not have to memorize that number. It is on the back of your periodic table. It will be on your unit and final exams as well. You just need to remember where to use it. Okay? So if you didn't do this, this is what I suggest. Take out a sheet of paper right now. Okay? Or if you got your notes package, have it there. Okay? And put this diagram on there. Okay? You need to know what parts of this heating curve use what formula. Okay? Or if you want, you can come up and snap a picture of it. Okay? I don't care, but you need this somewhere. Okay?